Hey everyone, welcome to our journey into the connected world. So before I get started, I want to give a special thanks to one of our graduate assistants, Hassan Aliwil, who put together the majority of this lesson and the slide set. Hassan is a certified, a Cisco certified network associate. So part of the challenge of this was actually kind of boiling it down to the basics and what we thought that you all needed to know about this thing we call the internet and the connected world, all the devices that we use over the internet. So without further ado, let's get into it. So welcome to the digital connected world. If you've ever wondered how Netflix shows streams instantly, if you've ever wondered why your online game sometimes lags, or if you want to dive into how this connected world that we live in actually works, that's what we're here to discuss today. So think about your daily digital activities. Maybe today you've already sent some messages over Snapchat or WhatsApp. You may have already watched a YouTube video. You may have made a quick digital payment with Apple Pay. Or if you're like me, you may have woken up this morning to Alexa telling you what the weather was. Oh, no, never mind, Alexa. Forgot I had it running on my computer. So all of these actions depend on complex networks working together very seamlessly, pretty much perfectly. But how does it all work? So let's talk basics. So imagine the internet as just this massive postal service. Every time you click something, three things are happening. One, your device sends a request to a server. Two, the server processes that request. And three, it sends back exactly what you need. Okay, hold on. What is a server? So a server is a powerful computer that stores websites, apps, and data. Really big websites that receive lots of traffic, well, they're actually distributing that load over a series of interconnected servers, distributed servers. So if you think about a website like Google, they actually have like an army of servers, and which Google server actually loads the google.com website for you is going to depend on your location. If you're in Northeastern America, you might get a server serving you from a state over, or maybe there are a lot of servers up in the New York area, rather than getting a server over in China, that it's going to have there's going to be a slower communication going on between your device and that server because of its distance. So now let's try to simplify this a little bit. So there are three key players in this process. There's your router. So think of this as the digital mail sorter. So when I'm trying to think of this as an example. So imagine your local post office. They receive, if you want to send mail out, then you might drop it in a mailbox, one of those blue mailboxes somewhere. Well, it gets picked up and it gets relayed through the postal service to your destination based on what? A unique address. Well, your router actually has a unique address. And so you send mail out to the postal service, and then how do you receive it back? Well, the person addressing you is going to specify your address on that return envelope. And so what's going to happen is someone has to sort that mail. And so you can imagine when your kind of postal service delivery person, when they put the envelope in your mailbox, that's kind of the role of the router in all this. So it sorts the mail based on who it's addressed to. So IP addresses, these are like unique postal addresses. And the servers, they're basically these massive digital warehouses. These are where we store what we need, the apps, the websites, whatever we're trying to access. So I have some visual aids to try to make this more clear. If I can just pull them up. So if you look at this first image, you can see this device we call the router. Think of the router. This is the device that sits between the devices on your local network or your home network and the wider internet. So here you can see these are what we call local IP addresses, meaning they're only seen by devices in your home. Outside your home on the internet, people have no way of accessing these devices via these addresses. So if you've ever had to connect a network printer, you may have seen something like one of these 192.168 IP addresses. So what's actually happening is the router, usually in conjunction with a related device called a modem, connects to your internet service provider. So some of you may have Comcast. I have Bright Ridge here in Johnson City, and that's what we call my internet service provider. And so my router, in conjunction with the modem, it communicates to the internet service provider when it's connected. And the internet service provider assigns it this unique public IP address. IP stands for Internet Protocol. And this IP address, this is the address that servers address me by when they want to send data packages back to me. So what happens is, let's imagine that this device, this is your smartphone, and you're on your home Wi-Fi network. So let's say you open let's say you open the Chrome app. And to load google.com, what happens is your smartphone sends a little data request to this router. This router is kind of like your postal service. It sees that you've addressed it to google.com, and it's going to forward this out to the internet service provider. The ISP, the internet service provider, they're kind of like your logistics. So they're going to push this out on the internet, and all these logistics, they're going to figure out how to get it to that end destination. And then that end destination, which is the server that hosts google.com, they're going to say, oh, somebody's requesting that I send them the data to load the google.com webpage. And they're going to send a response containing that data back to the ISP that has this address attached in the data packet. And that's going to arrive back at the router, and the router keeps track of who sent that original mail, which is this phone right here. So the idea is you can have all these devices sending requests to the router. Load YouTube, load Google, load Snapchat, and the router is going to send those requests out. The servers are going to respond, and the router's like your mail delivery person saying, oh, this mail's for you, this mail's for you, this mail's for you. It's the one keeping track of all that. But as far as what we see on the wider internet, everything goes through this one public IP address from your home. So in other words, all the requests from your devices route through the router. Why is it called a router? But there you go. Which is responsible for delivering the server's responses back to the device that the request originated from. So here's perhaps a easier diagram to visualize what's going on. You can see I stole this from Avast. So here's your internal network. And if these devices were just talking to each other without going out to the internet, then they could use these local IP addresses. this might be how you connect a network printer. So if you know your printer's address is, let's say it's 192.168.1.3, what you can actually do in Windows if you're adding a printer, let me see if I can pull this up. If I go to add device here, well, I gotta wait for it. I can click add manually, and you'll see I could actually type in add a printer using an IP address or host name. And I could type in that IP address of wherever my network printer is, and it would connect like that. You can find those IP addresses by actually scanning the devices on your network. There are scanning tools that you can use. But so these have their local addresses, and once again, they're basically making a request to the router. The router is responsible for communicating with the ISP, and the ISP is responsible for forwarding your request out to the internet, where the correct server is going to receive that. Okay. So let's go back into the slides. So let's talk about bandwidth. Speed matters. Bandwidth is like a water pipe. And that's what this picture on the right is demonstrating. So the bigger it is, the wider diameter we have, the more data can flow through. So we measure this speed in megabits per second, or even gigabits per second. Like my home network provider gives me a gigabit speed connection. That's through a special type of medium called fiber optic cable. Fiber optic does not use electrons, so if you think about what we call broadband and traditional kind of networking cables, that's all using forms of copper wire, particularly what we call twisted pair copper wire. And copper is a great conductor, and it's a very reliable medium, and it's totally adequate for things like our Ethernet cables that we use to plug in our routers or maybe do some wired networking within a building. But over vast distances, it's much slower than fiber because fiber is operating with photons or light, hence the word optic. Well, obviously, light is kind of the fastest traveling velocity that we know of in the universe. But it gets about, I want to say, I think it's about 67%. You might want to fact check me, but about 67% the speed of light is what photons can travel. That's how fast they can travel through fiber optic cables, which fiber optic cables, they're really made out of these very thin strands of silica, and they're shielded, and that's actually why there's actually a kind of global sand black market, is because the grade of silica needed to make things like fiber optic cables and electronics actually matters when we're making this types of equipment. Anyway, there's a little side tangent, but silica is a lot faster than copper wire, which means if you are able to get fiber internet in your residential area, that's becoming more common, then it's going to cost more, but you're going to be allowed to have more bandwidth. So bandwidth just refers to the maximum amount of data that can be transmitted over a network in a given time. So higher bandwidth, what this translates to in real terms is faster downloads, smoother streaming when you have more bandwidth, and when you have better bandwidth, meaning more consistent high speed, then you have less stream buffering when you're say, watching Netflix. Now, this is going to depend on what we call download and upload speed. So when you're streaming, when you're browsing the web, or when you're updating your games, this is all using your download speed. And this is why a lot of providers provide what's called asymmetric bandwidth. So that means they usually give you a higher download speed and they promise a lesser upload speed. Why? Well, for most folks, they're doing a lot less uploading. So that's every time your device sends a request, give me google.com, etc. Or when you upload a file, if you're sharing a file over the network, over the internet to someone, well, those would be examples of uploads. And then other services offer you symmetric, which means, at least in theory, you're promised to get roughly the same speed downstream as you do when you're sending data upstream. So, for example, they may promise that you get 350 megabytes per second download and upload, or 500 megabits per second down and up. Now, one thing that a lot of people complain about, and it's a very true phenomenon, is that internet service providers sometimes throttle your bandwidth. So sometimes at night, when a lot of people are on, you might notice that YouTube videos buffer more, and they might actually be throttling or kind of reducing your download speed to try to balance that demand. Sometimes it's outside of the bounds of what they're promising, and it can be frustrating because you feel like you're not getting what you pay for. But sometimes it can be kind of specified in the service agreement. So why Wi-Fi slows down? Let's talk about why things go slow. So we talked about bandwidth, and this can play a factor, of course. So if your service provider promises you 500 megabits per second versus me, where they promise a gigabit per second, I'm going to have the higher bandwidth, which means when I'm doing things like online gaming or streaming, that's going to help, especially when I'm doing things that require a lot of download speed. But another factor that's going to affect your the speed at which you could use your devices over the Wi-Fi is, well, the Wi-Fi router itself and your connections to that device. So for one, you can have too many devices connected, or bandwidth overload. Another thing that can happen is you have a weak Wi-Fi signal. So a lot of routers now don't just give you the 2.4 gigahertz Wi-Fi band. So this is the band that's been around for, well, since the beginning of Wi-Fi. We've been using this band. It's the same frequency band that Bluetooth operates on. It's a very reliable band for a home network connection or an office network connection because of this frequency. Now we also have a second frequency on most routers called 5 gigahertz. So that's a higher frequency. Now, what are the advantages of that? Well, at a higher frequency, you can basically pack more data per unit of time. It's a faster connection. But the trade-off is, and if you've taken a physics class, you're well aware, that higher frequencies are subject to interference faster. They basically deteriorate quicker, and so the distance matters a lot. And so when you're in the same room as the router, it makes good sense to have your Xbox console or whatever it is connected to the 5 gigahertz connection for a very fast, high bandwidth connection, because 5 gigahertz is capable of things like 600 or 750 or maybe even 800 megabits. Whereas 2.4 gigahertz is normally limited to around 350 megabits. And so that difference is vast. Now, but the difference with 2.4 is you can be several rooms over, separated by some walls, and that signal, because it's such a big waveform, it does not really get obstructed much, at least much, not nearly as fast as the 5 gigahertz. So that's why our routers kind of have both these days, is so that when you're close and there aren't many obstructions, you can have your devices connected to that 5 gig, and then your device that's 2 rooms over or downstairs could be connected to the 2.4. Now, the other funny thing about consumer grade Wi-Fi electronics is that they're typically made to broadcast the signal laterally and not vertically. And that's why sometimes, even if in real terms you're not far from the Wi-Fi router, but you're up a floor or down a floor from the router, you may have a very weak signal and things might buffer and get slow. Now, there is another problem, and it could be server congestion. So this is not to do with your Wi-Fi router. This is to do with the service providers, perhaps Netflix.com, perhaps your whatever video game that you're playing. That could be them getting overloaded. So a good example that comes to mind recently is Claude AI. So this is a service that I actually subscribe to, and at certain times in the day, often they have a little request that our server capacity is, or basically it's overloaded. Basically, there's a lot of traffic right now, and sometimes they'll say Claude is defaulting to concise responses due to a heavy server load. So what's going on? Well, that simply means that a lot of people like me are using the service at once. And actually with Claude, it's less of people like me and more about their integrations, where they have developers who have implemented it in applications they use. And those are using most of the server resources. So what that means is there's less for me, which means that sometimes when I type a chat and I see that high server volume message and I hit enter, sometimes that fails and I have to reload, refresh, and sometimes even resend my chat. And that's called, what's happening behind the scenes is something called packet loss, when I have to send that chat again. Sometimes the networking does fail. Sometimes servers are receiving too much traffic at once, and they just can't keep up with that volume. I guess it would be kind of like akin to, if we go back to that bandwidth page, they're getting blasted with this fire hose when they're only equipped with the server capacity to handle a steady stream like this. And this can happen when apps and services grow in popularity too quickly. And that's been the case with a lot of these AI tools. And it can also happen in terms of outages. So, sometimes Amazon Web Services, they've had a major outage before. So they're service providers for a lot of major companies, Amazon is. And so Netflix has a lot of servers in the Northeast that run on Amazon Web Services. D2L, if you've ever uploaded something to Dropbox, that's actually Amazon Web Services in the background. And so when they had a major outage in the Northeast and the Southeast one time, kind of the East Coast, they had a major outage one time. And it meant that not only were you having trouble uploading files to Dropbox, so I was getting emails, I can't submit my work. What was also happening is that some of the Microsoft logins weren't working. What was also happening was that if you got home from work and you're ready to stream some Netflix, you may have gotten some kind of error message that you couldn't connect to the server, or it may have just been buffering. And so sometimes that's what's going on, is that congestion. And then what can also happen, and this goes along with too many devices connected, is background apps. So apps that are using Wi-Fi to make requests in the background. And so, you know, if I have Amazon Alexa on my phone, what could be happening? Nope, ignore me. I triggered it again. What could be happening is that it's actually every once in a while making a request back to its kind of Amazon home server, and maybe trying to check if I have any new reminders or if I have anything new in my calendar, so that if it needs to notify me by putting up a push notification, you have a meeting at 12 or whatever, then it's able to do that. But if you think about all the apps you use, if they're all doing things like that, making little requests out over the internet repeatedly, and you have a lot of devices connected on the Wi-Fi, that could be why it starts to slow down. So let's talk about streaming services. When you hit play on Netflix, the service actually takes the video that you want and it breaks it into small packets, small units of data. So here's a book I have right here. And if I wanted to describe this book to you in a summary, well, I could do something like I could break it up chapter by chapter, right? I wouldn't just want to give it to you all as one big incoherent mess. Well, this is what servers are doing. So they're saying, you know, I can't send all the data at once. If I want to tell you about this book, I can't give you all the information in one big jumble. I need to divide it up by chapters. And so the server dices it up into small packets and it sends them in sequence to your device. So they stream to your device in real time. So you're always receiving the next packet that you need to play the video. So this is the process of streaming. It means that you don't just download the contents of the entire video and then play it. That's more how other video playing services work. Especially in the earlier days of the internet, you would wait, it's called buffering, you would wait and wait and wait while in the background the server keeps on grabbing the next chunk of the video until the whole video is loaded, and then you can play it. Whereas something like Netflix, they're kind of sending the data to you in a continuous stream as you go. For those of you in the first week who had trouble playing the audio, the digital literacy audio, the podcast audio, that's what was happening in the background, was that buffering was happening, where instead of just downloading a little bit and letting it play and then downloading the next bit while your podcast is still playing, it was trying to download all of it at once. And so it was like, come on, it's not loading. So your device reassembles these packets in the correct order, and it's just basically, when you have that high bandwidth fast connection, it's just a seamless, smooth video. You don't know that behind the scenes it's actually being loaded on the fly. It's kind of like me with this class. I'm building the plane while I'm flying it. I'm making the content as the course is developing. So let's talk about online gaming and ping. So ping is the time it takes for data to travel from your device to the game server and back. So this is very important to gamers. You want that high ping. You want that low ping so that you can have a smooth gaming experience. That's going to affect your competitiveness, right? If the frames are not synced up, if you are just having a laggy connection, that's going to make it harder for you in the game. So low bandwidth or the distance from the game server has an impact. So with really big websites and applications and services like Google and Microsoft, they have servers all around the world. But sometimes your game companies, well, they might only have a few dedicated servers for their games. And so, for example, if you're playing a game that has servers located in Eastern Europe and nowhere else, then you're going to have more lag than Eastern European players, for example, or perhaps even some that are kind of in the Western Asia area. And so ideally, what you have is a system where you get routed to a server in closer proximity to you so that you can have a good game experience. Now, once again, this is affected by devices on the same network. So if you have a Wi-Fi router that's basically bottlenecked from too many devices, or like we were talking about earlier, you don't have enough bandwidth, then that's also going to affect that ping. Now, before the game starts, players wait in the lobby, and this is where several things are actually happening behind the scenes. So in matchmaking, the system finds players with similar skill levels and ranks. So there's a data request. You make a request going out to the server. It says, here are my player stats, little packets of data that has your player stats in it. And that's going to get sent to the matchmaking server. The matchmaking server is going to root through your stats. And it's going to look for players with kind of similar stats. And once it has that together and say these players are online, they're ready to play this game, and they have these stats, then it's going to kind of try to divide them up and say, okay, now I have all the players. Here's team A, team B, or whatever. And then it's going to select the best game server based on ping and location. So it's going to look at where are these people located. Okay, it looks like they're mostly located in, let's say, the central United States. Well, we have a server in Texas. So we're going to choose that game server so that everyone has the best ping. And then what's going to happen is yet another set of server responses happen where they're sending the game assets back. And so this is kind of a continuous cycle where they have to do all these things in order before you can even enter your game. They have to kind of matchmake you, they have to select the right server, and they have to actually download, you're actually downloading to your computer the game assets, and they're downloading once again in those little packets and assembling them in order. Well, this all happens really, really fast. And then you play the game. So pro tip for our gamers, a wired connection, so that's an Ethernet cable, is faster and more stable than Wi-Fi. So you can definitely these days get away with that 5 gigahertz Wi-Fi connection if you have a good solid bandwidth router and you're close to it. But the wired connection is typically always going to be a little bit more stable. So let's talk about cell service and what the deal with 5G is. So as time has gone on, we moved through these different generations of cell service. 1991, we had 2G. Not much was going on in 1991. We did have SMS, or the main protocol that we were using for text message. There weren't a lot of people sending text message, as you can imagine. So our speed was pretty slow, 0.1 megabits per second. Well, think about today's speeds. So your Wi-Fi router today, it might do something like 350 megabits per second, might do 750 on 5 gigahertz. Well, we moved to 3G. So this comes out in 1998, but actually this is the dominant generation that we were on throughout the 2000s, kind of the early 2000s. Like my parents' phones, you can see 4G in 2008. Well, my parents were still using 3G in 2008. And so you can see we're getting 0.1 to 8 megabits per second. This gets better over time as we move toward 4G and we start to enhance the 3G networks. And by the time we get to 3G networks, now we're getting to the point where kind of in the middle of 3G, 4G, now we're getting to the point where we can pretty reasonably get video playback from YouTube, and if you remember, like Google TV. This is where these started to get more popular because, well, you could actually play it and it's not a grainy, very low quality image resolution. Well, now we're moving into the world of 5G, where we can get as much as a gigabit per second. So this is almost like we're capable of almost like getting a fiber internet connection worth of speed, which is kind of crazy. Now, this varies quite a bit, meaning there are different kind of 5G is actually an umbrella of related technologies that work together to basically deliver a very, very fast connection to you. And so if you're in a rural area, you're probably not getting like this super fast like gigabit, but you're still getting a very fast connection as opposed to 4G. Whereas if you're in a metropolitan area that has the millimeter bandwidth beacons, where you have beacons on every block, that's kind of like having 5 gigahertz Wi-Fi channels near you all the time, then you kind of have this architecture that, yeah, you're going to get a very, very fast speed. And so, but 5G by and large, because of this umbrella of related technologies, where we're kind of like meshing together these very fast, high bandwidth, high frequency beacons in dense population areas, and then we have this kind of infrastructure of smaller cell towers and then wider or larger cell towers further out, then we have this basically this really nice kind of web of interconnected infrastructure that makes it really, really fast. So this is a really compelling technology for self-driving cars because of that high bandwidth. If we ever, and we will get to this point, but as we're approaching this era where we can have autonomous cars that are driving themselves, well, they're responsible for communicating with each other on the road so that the thing all works, so that everyone's safe. And so we need a very high bandwidth, reliable connection to the 5G infrastructure for this to actually work. So yeah, 5G 10 times faster than 4G. It does need more cell towers. So I was talking about this series of technologies where you have these smaller cell towers and then you have larger cell towers. And not all areas have good 5G coverage yet. It's still a developing technology. It still needs a lot of infrastructure to make it all happen. It's not just magic. You know, people talk about the cloud. Well, no, it's real infrastructure. So let's talk about some myths versus the reality. So people say 5G is dangerous. I don't know what people say. It spreads COVID. It fries your brain. Well, what people don't realize is that even on the highest frequency end of 5G technologies, which is millimeter bandwidth, UV radiation is still higher energy. It's still a higher frequency. So millimeter bandwidth can actually penetrate kind of the first layer or two of your skin, but it kind of stops there. And so there is some concern where people are saying, well, look, if you're close to something that high frequency, we don't know. We haven't used this in telecommunications in the past. We've used lower frequencies. But by and large, you know, this is like, you know, you're walking outside, you're soaking up the majority of energy from the sun is kind of beyond the visible spectrum in UV. You know, that's a higher frequency. And so it's not something to fear. It's not something that you need to stay up at night worried about the 5G, like, I don't know, whatever people are saying it does, frying your brain or whatever. I'm not saying to like live next to a high powered cell tower, but it's not what people make it out to be. And I mean, really, just pull up a graph of the electromagnetic spectrum. It's not hard to figure out. There's nothing sinister here. Okay, so let's talk about online payments. So let's talk about what happens when you tap and pay. So I go out to Starbucks, or I go to the place that serves sushi on main campus. I can't remember that, Main Bowl, right? And I get my sushi and I tap the card to pay, and it's like, it takes a couple seconds. Most of that's probably not even the networking needed. Most of that's probably the scanner. I don't actually know. But point is very, very quick. So what's actually happening in this process? Well, number one, when you pay, your card sends an encrypted request. This gets relayed. So think about that process where we're relaying this through the router. And we're ending up on one of the bank's servers. The bank verifies the funds in your account. So the first thing is we take your card data and we say, oh, that's Discover card. So we'll send it up to the Discover account. And if it's a debit card, then it's going to go to the bank, right? Because the debit is linked directly to your bank account. So the Discover service is going to say, oh, that card is linked with such and such bank. And then it's going to check the funds. Once it sees that you have enough funds, then it's going to send a response back to that card holder. And then that card holder is going to send the response back to whatever the payment service is. What is it that people use? Clover or Square or whatever it is. And it's going to tell it that basically you have the funds, and then it's going to approve your payment. And it's all just happening in seconds, very, very fast. And so this diagram is to help visualize what's happening there. So there's this card network, basically, that can communicate with the bank that issues that card. And I said Discover. Most banks will issue like one of these Visa, American Express, or maybe MasterCard. And there's encryption used behind the scenes, so that data is scrambled in transit. It's not decrypted until it arrives at these networks where we actually do the checks. So in terms of data security, we have to encrypt data that's in transit. That means while we're sending it across the internet. And if we're storing it, like if the card network is logging any of that, or the issuing bank, they might have to store your card details, right? Well, we have to also encrypt data that is being stored. So those are the two places where it matters. When we decrypt the data and we use it, that's temporary. We need to delete that decrypted data so that your information isn't exposed. So let's talk about kind of real world, why this matters. So understanding our connected world helps us solve common tech problems, make better use of our devices, and stay safer online. It helps you appreciate the technology we use every day. So if you want to test your own internet speed, you can go to this website, fast.com. This is one of many services like this, and this will tell you what your speed is. So 21 megabits per second, and you can record your results. And remember what we talked about, bandwidth. That's what we're analyzing here. So 21 megabits per second, well, that may not be enough bandwidth that you need for high bandwidth activities like gaming. It may affect your streaming quality, especially if that bandwidth is being distributed and shared across a bunch of different devices. So in conclusion, the digital world is very interconnected. From streaming movies to online gaming, every digital interaction that you do relies on networks and data transmission. The internet, mobile networks, servers, these all work together to give you these seamless experience. So when next time you go on Netflix or start an online game and things start buffering, remember some of these things we talked about. Maybe someone else is streaming your house and it's too much bandwidth. Maybe you just need to be closer to the router or use a wired internet connection. or maybe your service provider simply isn't giving you enough bandwidth for what you're trying to do. These can all help you when you're trying to troubleshoot and figure out what's going on. So thanks for joining me on this journey through our connected world. I hope this video has helped.